Okay, in this video we're going to look at transformers. They're an interesting application of AC circuits that doesn't happen normally for DC circuits. So let's look at what a transformer is. When we say transformer, we don't mean the Autobots or the Decepticons, we mean a circuit component, unfortunately. So as you can see in this little picture, transformer, this is just a sketch of what one looks like, but you'll see that there's a wire going in that wraps around this core, this iron core, and there's another set of wires that wrap around the same core. So really it's like kind of like two inductors, two loops of coil around an iron core. And as we've seen before, that if we have a changing voltage, so if this guy has a changing voltage, we're going to produce a current in the wire, and that current's going to be a changing current. This is what we call, in one aspect, an AC circuit. So if we have an AC circuit, this changing voltage gives us a changing current, and this changing current gives us a changing magnetic field. And by changing the magnetic field, we actually change the flux. So the change in the voltage is equal to the opposite of the number of coils times the change of the flux over the change of time. So how fast the flux is changing in a certain amount of time. And the number of coils means that we have each bit of change of flux that we get, because there's a certain number of coils, each coil adds together. So we multiply it by the value of the coils, the number of coils. So this flux is going to travel along through the wire to the other side. It's going to get picked up by the other set of coils. And that other set of coils is going to obey a similar principle. It says that if we have a changing flux in a certain amount of time, it's going to see a change in its voltage. And again, it's going to be proportional to the set of coils. So if we combine the two equations and we assume no losses, which is an assumption, it's not actually true for most transformers, but for a perfect transformer, we're going to assume no losses, we'll see that this term, the delta phi sub b over the delta t, the change of flux with respect to time, is going to be the same in both equations. So we can solve the two and combine the two together. And we'll see that the voltage, the change of a voltage of one, will be equal to the change of the voltage of the other times the ratio of the coils. And we'll see that the number of coils for the pickup and the other ones are the source, or the secondary coils and the primary coils. Now this has one other interesting consequence, and it's because the power through this, the first coil, has to be equal to the power through the second coil, we're going to actually get another set of equations. And really what it comes down to, by equating the powers, we can get that the current in one times the change in the voltage of one is equal to the current in the other times the voltage in the other. And that actually has some really interesting and kind of nice consequences. Well, most transformers that we have don't have the same number of coils on both sides. They actually have different sets of coils. So we'll define what we call a step-up transformer. That step-up transformer is one that has a larger number of coils, secondary coils, than primary coils, or the coils that pick up the change in flux are larger in number than the ones that produce the flux. It looks something like this, where we have, in this case, 1, 2, 3 coils here, and here we have 1, 2, 3, 4, 5, 6 coils in this one. So we step up from 3 to 6 coils. And we'll see, for an example, if we have 1 amp coming in on this one and 120 volts, N1 is equal to 3, N2 is equal to 6, and we'll see that in this case what's going to happen is that as the voltage increases, we'll see a corresponding drop in the current. And if you ever know, if you've known around your house, you might have high voltage power lines. And high voltage power lines means that our current is a little bit lower, which actually means that it's easier, the lower the current, the less loss that we're going to actually see over a power line. So it's more efficient to have a very large voltage on the wires with a small current. So we'll see that you'll see these big transformers in your power plants, so they can send the electricity to your house in an easier way. And the step-up transformers they use is much, much more. You'll see ratios of 10 to the thousands. So the secondary coil may have thousands to having only maybe 100 on the first. So high voltage wires can have some very high voltage. Now when it gets to your house, we have to go through what's called step-down transformer, and that's where we do exactly the opposite. So we reverse everything. Our primary is now a lot of coils, our secondary is a lower set. And we'll see that if we were to start with the same conditions, 1 amp and 120 volts, now with 6 as our primary and 3 coils as our secondary, that we're going to get 2 amps out, so our increase in current happens at a loss of decrease of voltage. So transformers that you see, from the power plant, we step up to increase the voltage for efficiency, and then so we don't injure people and get more current. When we get to the house, we step down outside of your house. And you'll actually see these transformers, these are the ones that you'll see up on the telephone poles. The step-up transformers are normally in a giant lot separated by a fence, and has a nice 120 volt or 60 hertz buzz next to them.